Have you ever wondered how a massive metal tube weighing hundreds of tons defies gravity and soars through the sky? The science of flight is a fascinating blend of physics and engineering. At its core, flight depends on carefully designed wings that create lift as air flows around them. Flight is made possible by balancing four fundamental forces: lift, which pushes the aircraft up, weight, which pulls it down, thrust, which propels it forward, and drag, which slows it down. Modern aircraft are engineering marvels, with countless systems working in harmony. From passenger cabins to cargo holds, fuel systems to landing gear, these flying machines are among humanity's greatest technological achievements. The cockpit is the brain of an aircraft, filled with sophisticated displays and controls. Pilots manage these complex systems to navigate safely through the skies, assisted by advanced automation. The aviation industry is evolving to meet environmental challenges. Sustainable aviation fuels produced from renewable sources are one way the industry is working to reduce its carbon footprint. In this video, we'll explore the fascinating science of flight, examining the forces that keep planes in the air, how pilots control aircraft, and the cutting-edge technologies shaping aviation's future. Lift is the upward force that opposes gravity, allowing a plane to stay airborne. The wings of an aircraft are shaped as airfoils. Air flows faster over the curved upper surface of the wing than the flatter lower surface. This difference in speed creates a pressure difference, with lower pressure above the wing and higher pressure below, resulting in lift. The angle of attack is the angle at which the wing meets the incoming airflow. Increasing the angle of attack generally increases lift, but too much can cause a stall. When the angle of attack becomes too steep, airflow separates from the wing's surface. This reduces lift and causes a stall, as shown in this graph comparing a clean wing to one with ice. Modern aircraft use various technologies to optimize lift performance at different speeds, such as adjustable flaps and slats. Understanding lift is crucial for pilots and engineers to ensure safe and efficient flight. The second force of flight is weight. Weight is the force of gravity pulling the airplane towards the Earth. Let's look at all four forces acting on an airplane. As you can see, weight acts downward, directly opposing lift. Weight is directly proportional to the mass of the aircraft. It follows the simple formula: weight equals mass times gravity. Let's look at a practical example. A Boeing 737 has a mass of about 41,000 kilograms. On Earth, with gravity at 9.8 meters per second squared, its weight is approximately 401,800 newtons. Weight distribution is critical in aircraft design. Engineers must carefully balance the weight throughout the airplane to ensure stability and control. The center of gravity, or CG, must be within designed limits. A forward center of gravity makes the aircraft more stable, but less maneuverable. An aft center of gravity does the opposite, making the aircraft less stable but more maneuverable. To maintain level flight, the lift generated by the wings must equal the weight of the plane. When lift and weight are balanced, the aircraft maintains a steady altitude in level flight. Aircraft designers must carefully consider structural integrity to support the weight, reduce weight where possible for fuel efficiency, and include weight margins for safety. Let's explore thrust, one of the four essential forces that keep an aircraft in flight. Thrust is the force that propels the airplane forward, directly opposing drag and enabling the aircraft to move through the air. Thrust is generated in two primary ways: through jet engines or propellers. Jet engines work by sucking in air through the front intake, compressing it in the compressor stage, mixing it with fuel in the combustion chamber, and igniting it. The hot, expanding gases then exit through the rear of the engine at high speed, creating forward thrust. Propellers, on the other hand, act like rotating wings. Each propeller blade is shaped like an airfoil. As they spin, they create areas of high and low pressure, pushing air backward and generating forward thrust for the aircraft. Thrust is a perfect demonstration of Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. As the engine pushes air or exhaust gases backward, the aircraft is propelled forward with equal force. This fundamental principle is what allows aircraft to move through the air. Different aircraft use various thrust systems depending on their size, purpose, and required performance. Commercial jets typically use high-power turbofan engines. Regional aircraft often employ turboprop engines, while small private planes commonly use piston engines with propellers. No matter the method used to generate it, thrust remains one of the four critical forces that enable aircraft to fly, working alongside lift, weight, and drag to create the marvel of aviation. Drag is the force that opposes thrust caused by air resistance. It acts in the opposite direction of motion, slowing the aircraft down. Several factors affect the amount of drag an aircraft experiences. These include the shape and size of the aircraft, the speed of airflow, and air density. Aircraft designers use streamlined shapes to reduce drag. As shown in this comparison, a streamlined shape can reduce drag by up to 95% compared to a flat plate. There are three main types of drag that affect aircraft. First, form drag is caused by the shape of the aircraft pushing through the air. Second, skin friction drag results from the friction between air molecules and the surface of the aircraft. Third, induced drag is created as a byproduct of lift generation and increases significantly at higher angles of attack. Understanding and reducing drag has important practical implications for aircraft design and operation. Modern aircraft use advanced aerodynamics and undergo extensive wind tunnel testing to minimize drag and optimize fuel efficiency. Aircraft controls allow pilots to steer their planes through the three-dimensional space of the sky. Modern aircraft have several control surfaces that allow pilots to maneuver the plane precisely through the air. Aircraft move along three axes. Pitch is up and down movement. Roll is tilting the wings from side to side. Yaw is the sideways movement of the nose. Let's start with ailerons, which control the roll of the aircraft. Ailerons are hinged control surfaces attached to the trailing edge of the wings. When one aileron moves up, the other moves down, causing the aircraft to roll. This differential lift creates the rolling motion. Next, elevators control the pitch of the aircraft. Located on the horizontal stabilizer of the tail, elevators move up or down when the pilot pulls or pushes the control column. When the elevator moves up, it forces the tail down and the nose up, causing the aircraft to climb. Conversely, pushing forward lowers the nose for descent. The rudder controls the yaw of the aircraft. Attached to the vertical stabilizer or fin, the rudder is controlled by foot pedals in the cockpit. Pressing the left pedal moves the rudder left, causing the nose to yaw to the left. The rudder is especially important during takeoff and landing in crosswind conditions. In addition to control surfaces, pilots use power controls to manage the aircraft's engine. The black throttle lever controls engine power by regulating fuel flow. The red mixture control adjusts the ratio of fuel to air entering the engine, which is critical for efficient operation at different altitudes. These controls allow the pilot to manage airspeed and climb rate. Skilled pilots coordinate all these controls simultaneously. During a turn, for example, the pilot banks the wings with ailerons, coordinates the turn with rudder input, maintains altitude with elevator adjustment, and manages airspeed with the throttle. This coordination creates smooth, efficient flight through the three-dimensional airspace. Aviation is rapidly evolving with a strong focus on sustainability. The aviation industry is working to reduce its environmental impact through multiple innovative approaches. These include alternative fuels, electric and hybrid aircraft, improved operational efficiency, and advanced lightweight materials. Alternative aviation fuels, also known as sustainable aviation fuels, or SAF, are a key component of reducing aviation's carbon footprint. These fuels can reduce carbon emissions by up to 80% compared to conventional jet fuel. This graph shows historical emissions and projected scenarios based on adoption of sustainable technologies. Several types of sustainable aviation fuels are being developed and deployed. These include biofuels derived from plants and agricultural waste, synthetic fuels produced using captured carbon dioxide, alcohol-to-jet fuels, and hydrogen for future aircraft designs. This graph shows projected fuel prices under different sustainability scenarios through 2050, highlighting the economic aspects of transition to cleaner fuels. Electric and hybrid electric aircraft represent another important advancement in sustainable aviation. These aircraft are particularly well suited for short-distance flights, offering zero or significantly reduced emissions and lower noise levels compared to conventional aircraft. Looking to the future, aircraft manufacturers are developing revolutionary new concepts for sustainable flight. This includes designs like the Airbus Zero, a concept hydrogen-powered aircraft that could enable zero-emission flights while maintaining the speed and range capabilities needed for commercial aviation. Sustainable aviation offers numerous benefits beyond just environmental improvements. These include reduced greenhouse gas emissions, lower noise pollution, decreased dependence on fossil fuels, and the potential for lower operating costs in the long term. As the aviation industry continues to innovate, sustainable technologies will play a crucial role in reducing environmental impact while meeting growing demand for air travel. Artificial intelligence and automation are transforming modern aviation in unprecedented ways. AI is being used to improve safety, efficiency, and airspace utilization. Advanced systems can predict maintenance needs and optimize flight operations. Modern cockpits are being transformed with advanced technologies like touchscreen displays, augmented reality systems, and voice-controlled interfaces. These systems enhance pilot capabilities, making flying safer and more efficient than ever before. Heads-up display technology projects critical flight information directly into the pilot's field of view, providing real-time data and navigation assistance. This significantly improves situational awareness and allows pilots to maintain visual focus on the external environment, even in challenging conditions. Modern autopilot systems can handle complex flight operations, including takeoff, navigation, and landing, with minimal human intervention. These systems optimize routes, avoid adverse weather, and significantly reduce pilot workload during long flights. Artificial intelligence is revolutionizing air traffic control by predicting traffic flow patterns and identifying potential conflicts before they occur. AI systems can optimize takeoff and landing sequences, increasing airport capacity while reducing controller workload and maintaining safety standards. AI is transforming pilot training through advanced flight simulators that analyze performance patterns and provide personalized feedback. Studies show that AI-based flight simulator training can reduce the number of flight hours required for students to complete their training, making pilot certification more efficient. AI and automation continue to transform every aspect of aviation, enhancing safety, efficiency, and training, while paving the way for the next generation of flight technologies.